Welcome to the Ultrahuman experience. This session is free for you for the complete experience. Please download the Ultrahuman app.
Good evening, class. I am Professor Adam. I welcome you to this first lecture on Euler's theorem, named after the Swiss mathematician Leonhard Euler, who devised it. I'd like to remind you that the contents of this lecture are developed to assist you in gently drifting away into the land of fantasy, dreams, and restful sleep. For what is more soothing than the swirling of numbers and mathematical symbols around your head? Pi, delta, theta, sine, cosine, and so on, and so forth. Symbols that dance gracefully with each other and magically transform into other symbols, which in turn weave in and out of equations effortlessly. Such is the beauty of the world of mathematics. I'll give you a minute to get yourselves settled and rest your head comfortably, and then we'll begin today's lesson on Euler's formula. First, I'm happy to tell you that the technical information needed for this lesson is almost negligible. That is, you really need not know anything about what I am going to discuss. If you just happen to find my voice soothing, go ahead. Let that feeling take over you. I am often told, in fact, that I have a calming, pleasing voice. On the other hand, if you'd rather just follow what I will be lecturing you on, then go ahead and do that. It's entirely left to you. You call the shots here. All right, then. Let's begin. So, Euler's formula. Well, what is it? Now, simply put, this. E raised to the power I into pi plus 1 is equal to 0. This is its basic form, where E is Euler's number, I is the imaginary unit, and I'm sure everyone knows what pi is. This equation right here is the Euler's theorem. And so is this. F plus V minus E equals 2. And so is this. E of Z is equal to Z into 1 minus 1 by P into 1 minus 1 by Q into 1 minus 1 by R. They're all different variations of the same theorem. Now, in technical terms, I would say that Euler's theorem simply generalizes Fermat's theorem to the case where the modulus is composite. But since you probably haven't come across Fermat's theorem before, let's just examine the theorem directly. In its trigonometric form, the theorem states that e to the power ab is equal to cosine b plus a into sine b, and e to the power minus ab is equal to cosine b minus a into sine b. So how does this work? And why is it important? We all know by now, I hope, that sine and cosine waves can be found everywhere. We find these waves in sound, in water, in circuits. In fact, you'll see them all the time if you study electrical engineering. This little equation, believe it or not, is used in quantum physics as well. But what does it do? It relates this complex exponential, which can be any complex exponential, to sine and cosine functions. You'll notice that the cosine comes first. Why? I think you should be able to guess, as long as you didn't miss my class on real and imaginary numbers. In such equations, the cosine function will be a real number, while the sine function will be imaginary. In physics, that means that the cosine function will always have real-world implications. And on the other side, we have the sine functions, which are usually imaginary values. Speaking of real-world implications, let me give you some real-life examples to show you how this actually works. This very simple example will help illustrate Euler's theorem. Now, all this formula really says is, if you draw some dots and some lines between them, like a graph, and if none of these lines intersect, you have what is called a planar graph. And your graph should be a connected graph, that is, a closed shape. So Euler's theorem simply states that the number of dots minus the number of lines plus the number of regions it creates, including the outer region or the negative space, will always be 2. Now, there's a little bit of history to know here. When Euler discovered this theorem, he was actually talking about three-dimensional polyhedra. And it was only later translated into this form, which you've noted down. So, instead of saying dots, we say vertices. Instead of saying lines, we say edges. And instead of saying regions, we say spaces. Hence, we write Euler's theorem as V minus E plus F equals 2. Now we come to the interesting part. Euler's theorem requires the use of a function known as the Euler phi function, or totient function, denoted by this symbol. We are getting into the juicy bits of mathematics here. Let n be any positive integer. Then, by definition, there are numbers in n that are relatively prime to n. If a and b are two of these numbers, then so is ab. This follows from Euclid's lemma by contradiction. Now let's take AB. Suppose AB was not relatively prime to n. then there is some prime, let's call it P, that divides AB and divides N. Now, we know Euclid's lemma, so let's take P, which must divide A or B. Now, if, for example, P divides A, then A and N both have P as a factor and are not relatively prime. This contradicts our assumptions. Hence, we've managed to prove that AB is relatively prime to N. So, can everyone get all this into their notebooks? If some of you are still confused, don't worry. In the next class, I'll show you examples of how this works along with Euler's theorem. First, let's go back to our planar graph. You'll notice these spaces between them. Now, let's take the middle point of each space. And then we connect these dots. Then we have what is known as the dual graph of the original graph. And as you can see, you can make a dual graph out of pretty much any graph. But once again, looking at the graph, suppose we want to create a path. Actually, we should call it a set of edges which connects all the vertices of this graph, but without forming any cycles. What is a cycle? I think you know what a cycle is. A connecting shape starting and ending at one point. And the interesting fact is that the number of vertices in a tree is always one more than the number of edges. This is because you start with one vertex, and each new edge gives you another vertex to add to it. What is even more interesting is that the remaining edges give the spanning tree of the dual graph. The number of edges here is one more than the number of vertices of the dual graph. Here's a fact that you might find fascinating. This is regarded by many as one of the most beautiful formulas ever devised. Richard Feynman, the Nobel Prize-winning physicist, said this was the most remarkable formula in all of existence. He called it, and I quote, a jewel. He said it was, and I quote again, one of the most remarkable, almost astounding formulas in all of mathematics. Euler is even called the Mozart of Math. And the reason why this expression is so beautiful is because it combines 5 of the most important numbers of mathematics. 1. The basis of all other numbers. 0. The concept of nothingness. Pi, the number that defines a circle, and E, the number that underlies exponential growth. And last, but certainly not least, I, the imaginary, the square root of -1. But that is not all. This formula includes addition, multiplication, and exponentiation. Amazing, isn't it? It connects all of the important numbers and concepts in mathematics. And this, to many, is what makes it so beautiful. Now, as far as your examinations are concerned, you should be absolutely familiar with two things. First, how to find the Euler's number of any number. Second, how to calculate the remainder for a certain value using Euler's theorem. All the questions that follow will have a combination of the above two formulas. Basically, you will be using Euler's theorem to get information about the number without having to calculate using a lengthier method. Earlier, people would actually need to use Venn diagrams to calculate the answers. Can you imagine the amount of work that would take? Let me give you some quick examples so you know how to use Euler's theorem for basic questions. Let's start with finding the Euler's number for 20. What are the prime factors of 20? 2 and 5, if I am not mistaken. Now we just apply the formula. Here we go. We landed up with 8. What it means is that there are 8 numbers less than 20 which are co-prime to it. Shall we cross-check? We have 1, 3, 7, 9, 11, 17, and 19. Did I forget one? Oh, yes, 13. There you go. That's exactly 8 numbers. Quite a useful theorem, isn't it? Let's move on. The second type of equation that I want us to solve together is how to find the remainder of a division using Euler's theorem. Let's try to solve for 13 raised to the power 18 divided by 19. Now, here's a trick to remember. The Euler's number of any prime is always 1 less than the prime. Here, 13 and 19 are co-prime to each other. So the remainder is 1. But what if we want to calculate for, let's say, 13 raised to the power 22 divided by 15? Please copy this down. We're going to calculate the formula like so. And we can find the Euler's number, which in this case is 8. And the numerator can be written as 13 raised to the power 8 into 4. So once again, we find that the remainder is 1. Easy, right? The next thing that I want to talk about are the uses of this theorem. I did mention that the uses are vast, and that you'll find this theorem being applied in many areas of science. Fitting, considering that Euler himself was not just a mathematician, but also an astronomer, physicist, and engineer. He also had an interest in music theory. Like I mentioned earlier, his theorem has varied uses. Since it is a generalization of Fermat's little theorem, it's also usually applied in the same areas as that theorem. In this class, I will cover two areas where Euler's theorem works very well. The first is primality testing, and the other is the fifth root party trick. Yes, you heard me right. So let's begin with the contrapositive of Fermat's little theorem, which states that a to the power p minus 1 is equal to 1 mod p. If this congruence, please copy this into your notebooks. If it does not hold, then we can come to one of three conclusions. Either p is not a prime number, or a is a multiple of p. We know that a is much smaller than p, and hence we know that p is not a prime. So yes, this will tell us whether or not a number is prime. Now let's consider this equation. We have 2 raised to the power p minus 1. If this is not congruent to 1 mod p, then p is not a prime. But if 2 raised to the power p minus 1 is congruent to mod p, then it is still possible that p is a prime, isn't it? What we can do in this situation is try another value of a. Let's take 3, for example, and see if 3 raised to p minus 1 is congruent to 1 mod p. Before we go further, can everyone solve this? Just go ahead and give it a try and see if it works for you. Okay, so I assume you've had plenty of time. Coming back to our equation, if we have tried to disprove p and haven't yet managed to, we still have reason to believe that p is a prime. We don't yet know because it passed the first test. Now, the correct term for a number like p is a pseudo-prime, or officially, a Carmichael number. Numbers that are not prime but pass the primality test for all values of a as we have tried. Now, imagine if the number wasn't a small number, but let's say 1,000 or 10,000, or a very large number with thousands of digits. It wouldn't make sense to use this equation then, would it? Even attempting to find a raised to the power of p would be next to impossible. Of course, nowadays you have machines to do that for you. But we don't all have supercomputers sitting in our backyards, which is exactly why we try to find the value of mod p, which is much easier to find than a raised to the power of p. Now let's talk about the fifth root party trick. What's that? I think you're all familiar with it. It is a simple and quick way to know what a number is if you are given its fifth power. Please write down this equation. If you raise a 2-digit number to the fifth power, you can quickly tell what it is using this equation. What makes this trick work is that in base 10, the number n and its fifth power will end in the same digit. It's possible to try and prove this by trying all the possible last digits. We can go from 1, 2, 3, 4, all the way to 9. But there is another way if you want to make it easier. That's where Euler's theorem comes in. Let's take an example. Please write this down. So Euler's theorem shows that raising a to the power of 5 of m plus 1 in base m keeps the last digit the same, but only if a is relatively prime to m. Thus, the fifth root party trick works for all numbers in the 10th base, but to move it to other bases, one needs to use Euler's theorem. Can everyone write the proof down? These are the two questions which are most likely to show up in your final examinations, so I suggest you go through them carefully. The theorems are simple as long as you remember the original equation we had started with and derive the new ones based on it. Do try and find the time to look up Carmichael numbers as well. Now, before we end the lesson, remember that sometimes just taking some deep breaths can help take the edge off at the end of your day. It helps calm the mind, relax any tension, and clear your head before you begin your work. If you find yourself wandering, go on that journey, far away from your day and into a space that's completely yours. Let go. Relax and wander deep into sleep. Good night and sweet dreams.